When do clouds form? Well, we know, and we've seen, it's when it reaches its dew point temperature. Okay, so when does air reach its dew point temperature? Well, if we're looking at clouds, it's going to occur somewhere up in the atmosphere. Now, we have already seen that temperature, or we've learned that temperature decreases as you increase with elevation. We saw that in our discussion of layers in the atmosphere. So in the troposphere, the one we live in, air temperature decreases with elevation on the whole. So we're going to look at that in a bit more detail. How do we know what the temperature of the air is in the troposphere as you rise in elevation? Well, weather forecasters and meteorologists have been using these weather balloons for many, many years. And essentially, the fancy name is called a radiosonde, and instruments are attached to a wire at the bottom of the balloon, and they let the balloon go. And it rises through the atmosphere and takes measurements as it rises, as it increases in elevation. It takes measurements of temperature, relative humidity, wind speed, direction, and air pressure, as well as elevation. Okay, so here we have our weather balloon. And on this diagram here, we've got elevation on the y-axis and temperature on the x-axis. Now, we're going to start at sea level, or on the ground surface. And we've taken a measurement, and that measurement is 20 degrees centigrade. And what we're going to do is let that radiosonde, the weather balloon, go. There it goes. And as it rises through the atmosphere, it'll take a measurement. And so let's say at 500 meters, we've taken a measurement and it's about 16 degrees. It rises even further. There it goes. And at 1,000 meters, it takes another reading of the air temperature, and it's about 12 degrees centigrade. It rises even further, rises to 1,500, and it's about 8 degrees. It goes even further, it gets to 2,000 meters, and it's 0 degrees, and it goes even further to 2,500 meters, and it's about -5 degrees centigrade. Okay, so that's just the measurements of air temperature it's taken with elevation. And that's the change in air temperature at that particular point as recorded by that weather balloon. We give that a fancy name. We call that the environmental lapse rate. Now in your practical workbook, you can also do that by measuring the air temperature of different towns as you go up a mountain, but meteorologists do it with a weather balloon. It's called the environmental lapse rate. Fancy name, just means the change in temperature with elevation. Why is the environmental lapse rate important? Because an volume of air, or as air rises, it will cool. Now, up until now, we've been using terms like a volume of air or an amount of air. The proper term we should be using is a parcel of air. And we say things like, well, as a parcel of air rises through the atmosphere, its temperature changes and we might get a cloud. So before we go down that path, better explain what a parcel of air is. So a parcel of air is just an amount of air that has similar features, in particular similar temperature and humidity, than that air that is surrounding it. Now, of course, it's not like a balloon where you've got a solid boundary between parts of the atmosphere. It will grade into what is next to it. Generally speaking, you can often identify amounts of air that have similar characteristics. And a good example is if you've ever seen a large cumulus cloud rising into the atmosphere, you can say, oh, so what's the air that's around that cloud and in that cloud and the moisture vapor that's showing, that's the features in there are similar, and they're going to be a bit different to the features that are in the air that's adjacent to that cloud. Otherwise, it too, that air would also be forming a cloud. So we sort of put these lines around these parcels of air. Another way of looking at it, if you've ever looked at the rain radar from the Bureau of Meteorology, you'll see amounts of rain sort of moving along. Well, that's obviously the same, that part of the atmosphere there, that air has similar moisture characteristics, similar temperatures. Okay? So it's a bit conceptual, but it's important to sort of remember that air changes in the atmosphere, but you can get significant amounts of air that have similar characteristics. So that's what we call a parcel of air. All right, so with that in mind, let's see what happens when we raise a parcel of air through the atmosphere. But before we do that, what does he mean when he says air parcels rise? How can air rise? Well, we had one look at it earlier on when we looked at sea breezes, and we said as the surface is heated by the sun, that heats the air close to the Earth's surface and forces it to rise. So, with an amount of air near the Earth's surface, as it's getting warmed, it can be forced to rise. And if that continues to heat, then more air will be forced up and it will rise through the air that is around it. So that's one way, and we call that convection. Another way, which is a little simpler, another way which is a little more straightforward or easy to think about, is what happens when cold air meets warm air. And as we'll see a little later on, and if you're working through your practical workbook, you would have come across this term already. That's a front. A front is a change between air types or air masses or even parcels of air. And cold air, being cold, will go underneath warm air, and the warm air will be forced to rise. It will be forced to rise over the top of the cold air. Okay, so that's the second way. And the third way, which if you did any sort of geography, this one is a classic geography question, is when air is moving and it meets a physical boundary of a large mountain or any rise in topography. The air has to go somewhere, so it goes up. It's being forced up. And that process is orographic. We call that an orographic process. So that air parcel is being forced to rise because of a physical barrier. Okay, so with that principle of understanding that air can be forced to rise, let's look at what happens. All right, so we're going to take our rising parcel of air. Now, as it rises, it cools. Why does it cool? Well, we can look at it using this equation. Don't panic. We'll break it down and examine why it's useful. PV equals RT. It's the ideal gas equation. It's used in physics and chemistry. But you can also use it to understand what is happening in our atmosphere. P is pressure, V is volume, R is a constant, and we don't really need to worry about that constant at the moment or at all in order to use it to examine what's happening in the atmosphere, and T is temperature. Both sides of those equations always need to balance each other. Okay, so if you increase one on one side, you've got to do something on the other side in order to balance it. Okay, so let's have a look at some examples. What happens if we increase the temperature? All right, PV equals RT. We increase the temperature, so that's on that right-hand side. You must also then get an increase in pressure. That balances it out. Increase on one side, you have to increase the other side. The example is, you take an aerosol can, don't ever do this at home, you throw it in a fire, you're increasing the temperature of the gas in that can. Well, what happens? It increasing its pressure inside that can. You know that happens because eventually what happens? It explodes, and then suddenly the ideal gas equation comes in again. Once it explodes, then that pressure
is released and decreases,
results in an increase in volume. So either the pressure increases or the volume has to increase. And an exploding aerosol can is a good example of seeing a demonstration of how both of those things, how either of those things can occur. increase in pressure, or kaboom, an increase in volume. That gas is now everywhere and I've caused damage. What happens if we increase the pressure? So we're pushing the gas together and increasing its pressure. We're squeezing it. Well, we're going to decrease its volume. I'm just doing it with my hand. You increase the pressure, you decrease the volume. Think about a barbecue gas bottle, a propane gas bottle. We've taken this gas and we've increased the pressure to get it, and then we've put it in a bottle. So what was a big gas cloud of propane, we have been able to squeeze it down and put it into a gas bottle. Okay, so that's increasing pressure on the left-hand side. Therefore, we need to decrease the volume because it's also on the left-hand side. Okay, increase in pressure, you have to decrease the volume because they're both on the same side of that equation. What happens then if we decrease the pressure? Well, we're going to increase the volume. You open that gas tap, then that gas that was being compressed is now allowed to release, and it goes back out into a cloud of propane gas. But you can also balance that equation if you decrease the pressure by decreasing the temperature. So decrease pressure on the left-hand side, you want to balance that equation, you decrease the temperature. And if you've ever had a gas leak, hopefully not a dangerous one, but if you've ever found that your gas bottle is leaking, feel the metal valve or the connection. You'll often see it's really, really cold. And that's an example of the ideal gas equation coming into play. Decrease that pressure by releasing it. It will do two things. It'll increase in volume, but it'll also decrease in temperature. Ideal gas equation in action. All right, still with me? Hope so. Okay, now let's go back to our environmental lapse rate here. So the environmental lapse rate, we can now put the temperatures on of the air, of the environment, okay? No parcels rising yet. It's just the radio sonde, the weather balloon, that has measured those temperatures. All right. Let's put on our parcel of air. Simple black circle representing our parcel of air. For some reason, the conditions within that volume of air are similar and they're different to the air that's outside of that black line. Now, let's force it to rise. It could be one of those three ways: orographic, frontal, or convection. Whatever, let's just force it to rise and see what happens. So, at ground level, the temperature is 20 degrees. Right? The weather balloon is standing in the parcel of air, right? So it's the same measurement. So it's 20 degrees centigrade. Let's force it to rise. Now, as it rises and goes up to 500 meters, the air around it is 16 degrees, but the parcel of air isn't 16 degrees, it's 15. Because it's expanded a little, we know it's cooled, and it just happens to have cooled to 15 degrees.
I'm just going to jump in here because I realised in reviewing the lecture I didn't really explain something as well as I could have. So I've said that the air parcel expands as it rises. Now, why does it expand? It's because the air pressure above that air parcel decreases. There's less air pushing down on that air parcel. And so it's allowed to expand a little. What does that do? That increases the volume. And so via the ideal gas equation, if you increase the volume, you either decrease the pressure or you decrease the temperature. And so we've decreased in this example to 15 degrees.
What's going on here? It rises a bit further, gets to 1,000 meters, it expands a bit more, and by that ideal gas equation, it's now 10 degrees. It rises a bit further and gets up to 1,500 meters, it expands a little more, and it's at 5 degrees. It rises a further point to 2,000 degrees, 2,000 meters, So it rises further to 2,000 metres, it expands a bit more, and via the ideal gas equation, its temperature becomes 0 degrees. And then finally, it gets to 2,500 metres, it's expanded, and via the ideal gas equation, its temperature is -5 degrees. Just to make sure it's clear, why is that air expanding? Because there's less air above it. It's just being allowed to expand. And so that's one of the reasons why air temperature decreases with elevation, generally speaking, in the whole troposphere. But if we look at a parcel of air, if it's being forced to rise and continues to being forced to rise, so let's imagine it's going up a 2,000 or 3,000 metre mountain, as that air rises, it will drop in temperature according to the ideal gas equation. If you have a look at the environmental lapse rate, they're different temperatures at those same elevations. So that air parcel is at a different temperature to the air that's around it. That becomes important a little later on. Okay, so we can plot that line on this graph, and that's the green line. And you can see it's much straighter than the environmental lapse rate. So the name we give to the process of decreased temperature as an air parcel rises is called adiabatic cooling. And if the air parcel never forms a cloud, we call that the dry adiabatic lapse rate. Okay, so now you've got your environmental lapse rate, which is just the change in temperature of the atmosphere, and you've now got your dry adiabatic lapse rate, which is the change in temperature of an air parcel as it rises through the atmosphere, reducing in temperature as a result of the formula guided by the ideal gas equation. And it's a constant. It's always 10 degrees centigrade per kilometre. All right? So air cools at 10 degrees centigrade per kilometre, as long as it hasn't yet formed a cloud. And so we call that the dry adiabatic lapse rate. So let's have another look at this diagram again. This time we'll add an extra piece of knowledge. The amount of moisture in the air is around about 6 grams per kilogram of air. So its dew point temperature will be 5 degrees centigrade. So let's raise that parcel of air. And you can see that as it rises, it changes in temperature, it falls in temperature, pressure decreases, PV equals RT. And eventually, as it rises, it reaches 5 degrees centigrade. That is our dew point temperature. What happens then? We get a cloud forming because the water vapour has now reached 100% humidity, and so the water vapour gas turns into water droplets, and we get our cloud that we see. But then look at what happens if we continue to force that air parcel to rise. Whereas before, the temperature of that air parcel as it got to 2,000 metres was 0 degrees, look at its temperature now. It's not 0 degrees, it's slightly warmer. It's 2 degrees. And then at 2,500 metres, it was -5 degrees in our earlier example, but now it's -2 degrees. So this parcel of air must be different to the one we saw before, and the difference is the amount of moisture that is in this air parcel means its dew point has been reached
at 2,000 metres.
And then, forced to rise, we have a different rate of cooling. It no longer follows that constant 10 degrees per kilometre. It's different. It's changed. It's stayed a little bit warmer. Why? Why is it a little bit warmer? It's still being forced to rise. It's still expanding. But the ideal gas equation is no longer ideal. Something else is happening. Do you remember our discussion on latent heat of evaporation? Now you'll see why we talked about it all those lectures ago. Latent heat evaporation is hidden heat. It's hidden in that water vapour during the process of evaporation. During the process of condensation, that hidden heat is released into that air. and so it keeps that air parcel a little warmer. So we're still forcing it to rise, still going over that mountain, but it doesn't cool any longer at the dry adiabatic lapse rate. We say it's cooling via the saturated adiabatic lapse rate, and it will differ. It's not a constant, 10 degrees per kilometre, but because of that latent heat that's now gone into that air, it's kept a little bit warmer, and different air parcels will have slightly different saturated adiabatic lapse rates, but it's around about 6 degrees per kilometre. Dry, 10 degrees per kilometre, and constant, the saturated adiabatic lapse rate or wet adiabatic lapse rate is less, and so it stays warmer for longer. All right, see, latent heat evaporation. Okay, now, why is this important? Because having an understanding of the temperature of an air parcel as it rises through the atmosphere compared to the temperature of the atmosphere itself will tell us whether or not the air parcel will continue to rise by itself. Right? If you were to remove that mountain, would that air parcel rise? Now, a rising air parcel, we say, is an unstable atmosphere. If the air parcel doesn't rise by itself, we say the atmosphere is stable. Okay? So, we can look at this diagram here. What have we got here? We've got those 3 lines that we looked at. We looked at the environmental lapse rate, we looked at the dry adiabatic lapse rate, and we looked at the wet adiabatic lapse rate. If air is going to cool either by the dry adiabatic lapse rate or the wet adiabatic lapse rate at a greater rate than the air around it, than the environmental lapse rate, then it's always going to be colder than the surrounding atmosphere. So you will never get that air rising. It will never be warmer than the surrounding atmosphere, so it will never rise by itself. So that air will just stay on the Earth's surface. And we say that's absolute stability. Absolute instability is when the dry and wet adiabatic lapse rates are lower than the environmental lapse rate. So the environmental lapse rate there, in this particular location, remember I said it, the environmental lapse rate can change depending on the location. So the environmental lapse rate here is 12 degrees per kilometre, so every kilometre it's going to reduce by 12 degrees, but the dry and moist adiabatic lapse rates are less. So they will cool more slowly and so will stay warmer than the environment. So if that was the case at a particular point on the Earth's surface, then that air parcel would just rise by itself. Right? You might need a little push to get it up off the ground, so that was, at the moment, they're all 30 degrees, but even the slightest influence by convection or orographic or fronts will just mean then, once it's off, it'll go by itself, and we call that absolute instability. But then, of course, you can get something in between, and this is what occurs in most cases. Okay, let's have a look at what could actually occur in real life. All right, so here we have an example of our environmental lapse rate. This is an example of conditional instability. So we start off following our dry adiabatic lapse rate. So that air parcel rises and cools at that rate and changes in temperature as shown by the line. But then at 1,000 meters, it reaches its dew point temperature. And so it changes its rate of cooling and cools at a different rate. So it's still it has to have been forced up by something. So it's going up by a mountain, or convection is forcing it up. But as soon as it reaches 2,000 meters, the temperature of the air parcel is then the same as the air around it. And if it's forced up a little more, the temperature of the air parcel is now warmer than the air around it, and bang, we've now got an unstable atmosphere. So let's say it was being forced up by a mountain. If that mountain was only, let's say, 1,200 meters high, so the air got up to 1,200 meters, even if it had formed a cloud, it still wouldn't be warmer than the surrounding atmosphere, so it would fall back down. And we would say that that air parcel is stable. However, if the mountain range was more than 2,000 metres high and the air was forced up, and suddenly it cooled but was warmer than the surrounding air, then even if the mountain disappeared, that air would continue to rise in an unstable landscape. So this is a good example of where you can get stable and unstable in the same conditions, but it will only become unstable if that air parcel is forced to rise beyond that point. And we give those points particular names. The lifting condensation level is the fancy term we give to the point at which that air parcel reaches 100% humidity, the point it forms a cloud. And the level of free convection, another fancy term, is that elevation at the point where the temperature of the air parcel is warmer than the temperature of the surrounding air and can rise by itself. So I hope you've been able to stay with me and realise that there's a lot more going on than just fluffy white clouds forming up in the sky.